Topic 7.1 Summary Part 4 Alpha, Beta, and Gamma Decay. Recall that an alpha particle is a helium nucleus, and a helium nucleus, of course, consists of 2 protons and 2 neutrons, so it has a mass number of 4 and a proton number of 2. So here's an example. Let's take a look at an alpha decay. This is also going to serve to introduce us to our first nuclear equation. So in our example here, uranium-238, uranium-238 has a mass number of 238 and a proton number of 92. Uranium-238 undergoes an alpha decay by emitting an alpha particle, and when this happens, the uranium nucleus transmutates or changes into a thorium-234 nucleus. Let's take a look at the rules for nuclear decay. The proton number Z on the left side of the equation must equal the proton number Z on the right side of the equation. So on the left-hand side, we have the proton number for uranium is 92, and on the right-hand side, we have the proton number for thorium is 90, and the proton number for helium is 2. So 92 on the left equals 90 plus 2 on the right, so that balances. Now let's look at the mass number A. A on the left-hand side of the equation must equal A on the right-hand side of the equation. Well, the mass number for uranium-238 is 238. That's why it's called uranium-238. And the mass number for thorium is 234. And the mass number for helium is 4. So 238 on the left equals 234 plus 4 on the right. So I could give you a problem where perhaps one of those numbers was blanked out, and you should be able to look at the rest of the numbers and fill it in. Let's take a look at beta decay. There are 2 types of beta decay. In beta decay, the nucleus either emits an electron or it emits a positron. Remember, a positron is just like an electron, has the same mass, same properties, except it's positive. And when that happens, the atomic number is increased or decreased by 1. When we look at the equation in a minute, that'll make sense. The neutron number has an opposite change to the change in atomic number, and again, we'll see why in a moment. And the mass number does not change in a beta decay. So let's look at a couple of examples of beta decays. The top example here is an example of a beta decay with an electron being emitted. Sometimes we call this a negative beta decay. So we have carbon-14 with a mass number of 14 and a charge number of 6, changing into nitrogen-14 with a mass number of 14 and a charge number of 7, plus an electron with a mass number of 0 and a charge number of -1, and something called an antineutrino, which we'll talk about in a couple of slides. An antineutrino has no mass and no charge, so it doesn't affect the balancing of the equation. Notice, again, using our rules for balancing, the total mass on the left-hand side of the equation is 14, and on the right-hand side, the total mass is also 14. But if we look at the charge number, the proton number, on the left-hand side of the equation, we have carbon, which has 6 protons, and that changes into or transmutates into a nitrogen, which has 7 protons. But an electron, the beta particle, is given off. So on the left-hand side of the equation, we have 6 for the charge, and on the right-hand side, we have positive 7 plus -1, which of course equals 6, so it balances. If we look at the second example here, we have an example of a beta decay with a positron being emitted. So notice a couple of differences here. One is the symbol for the positron is a +1, so we have a number of +1 for the positron. And notice that the last symbol is a little different. The nu, which looks like a V, is a symbol for a neutrino. So here's some crazy stuff for you. During a beta decay, a neutron actually changes into a proton and an electron, or a proton changes into a neutron and a positron. Again, both the mass number and the charge number must balance on both sides of the equation, and if you study these 2 examples, you'll see that they do. Neutrinos and antineutrinos are required for energy and momentum to be conserved. Their existence was postulated by Wolfgang Pauli. We'll talk more about neutrinos and antineutrinos in just a bit. In a beta decay, the electron is always accompanied by an antineutrino. The symbol for an antineutrino is this letter nu, looks like a curved V, with a bar over the top of it. So a negative beta gives us an antineutrino. In a beta decay, a positive beta decay, a positron is always accompanied by a neutrino. So here we have a positron, and we get a neutrino. The symbol for neutrino is that nu with no bar over the top. And you need to memorize this, but let me just give you a trick here, okay? This is not anything physics related. This is just a mnemonic device for remembering, okay? When you get a negative beta, the negative beta, of course, has a negative sign. And you get an antineutrino, and the symbol for an antineutrino is this nu bar. The bar over the top of the antineutrino kind of looks like the negative sign for the negative beta decay, and those go together. On the other hand, in a positive beta decay, where you get a positron, you have a positive symbol here, no negative, so you get a neutrino which has no bar over the top, so you can think of that as having no negative. So our third and last type of decay is the gamma decay. And the gamma decay is a little different than the alpha and the beta because there's no transmutation. You have the same element after a gamma emission as you had before. Following an alpha or beta decay, the nucleus is often left in an excited energy state, symbolized by this asterisk. When the nucleus transitions to a lower energy state, a high energy photon is emitted. This is called a gamma decay. This is not terribly different in concept than an electron in a high energy state dropping to a lower energy state and emitting a photon. The difference is that inside the nucleus the energy levels are much higher, so when the nucleus changes from a higher energy state to a lower energy state, the particle that's given off, or in this case the ray, has a very high energy. The daughter product of a decay is usually yet another unstable isotope, so it will in turn decay into another element. This goes on over and over and over again, and this progression is called a decay series, and the decay series will eventually end when we get to a stable isotope. So if we take a look at this chart here, this is the decay series for uranium-238. So if we start up here in the top right-hand corner, we have uranium-238, which undergoes an alpha decay and turns into thorium-234. But look at that half-life here, 4.5 times 10 to the 9th years. So the half-life of this transition is 4.5 billion years. That's how old the Earth is. But eventually we have this thorium-234, and the thorium will in turn decay, undergo a beta decay, and turn into protactinium-234. So protactinium-234 is right here, and with a 6.5 hour half-life, protactinium-234 is going to turn into uranium, so we're back to uranium again, but now it's uranium-234. Uranium-234 will do an alpha decay to thorium-230 with a half-life of 2.5 times 10 to the 5th years. The thorium-230 will undergo an alpha decay into radium, and radium has a half-life of, this decay has a half-life of 7.5 times 10 to the 4th years. The radium-236 will undergo another alpha decay into radon-222. Radon-222 goes to polonium-218, and polonium-218 goes to lead-214, and so on down the line. It's kind of like a pachinko game. Eventually we get to the bottom left-hand corner here, where we have thallium-206, which turns out to be stable, and that's where it all ends. So this is called a decay series, and every radioactive element has its own decay series. Another interesting thing about a decay series is there are some branches here. So for example, if we look over here, when we got lead-214, lead-214 is going to undergo a beta decay to bismuth-214, but bismuth-214 can do a couple of things. It can do an alpha decay over here to thallium-210, or it could do a beta decay into polonium-214. So there's more than one way to get to the end, but the end is always going to be a stable element. That's all, folks. except I do have a wacky definition for you. Today's wacky definition is avoidable. Avoidable, what a bullfighter tries to do.